This is 2009 Form B, number 2. A storm washed away sand from a beach, causing the edge of the water to get closer to a nearby road. The rate at which the distance between the road and the edge of the water was changing during the storm is modeled by this function, in meters per hour, t hours after the storm began. So this is again, this is our rate, right, in meters per hour. The edge of the water was 35 meters from the road when the storm began, and the storm lasted for 5 hours. The derivative of this function is, well, we could have done that. Geez, why are they telling us that? And it's a calculator problem. What was the distance between the road and the edge of the water at the end of the storm? Well, let's see. The road, we started at 35, right? And then the rate is this function here. This is the rate that the distance between the road and the edge of the water was changing. So let's find, and I'm not sure, this is going to give us this is going to give us a negative number. So the end of the storm, that's from 0 to 5 of this. Again, the integral of the rate gives us the total amount of change. And I'm just going to make sure, I'm going to do that first and make sure it comes out to be negative, because we know that it's getting closer to the road, right? I think that the rate that they gave us is, will have a negative sign on it when it's getting closer, when that distance is dropping. Let's make sure. So, Math 9. And this is a rate, so I'm not using its derivative. I want to do fn int of square root of x plus cosine x minus 3, comma x, comma 0, comma 5. Thinking so hard. So negative 8.505. So that's 35 minus 8.505. So I was right to put a plus there, right? Because this was going to come out to be negative. So that gives me 26.495. 26.495. What is it, meters? So we started out 35 meters from the road. That's how much it changed, right? The integral of the rate. And now the water is 26.495 meters from the road. Using correct units, interpret the value of f prime, that's the derivative of the rate of 4, equals 1.007 in terms of the distance between the road and the edge of the water. Now let's see. The derivative of this, which is in meters per hour, would be meters per hour, right? Because this is already meters per hour. When we take the derivative of that, that's the rate of change of the rate, kind of like an acceleration. So 1.007 meters per hour. So that's the rate of change of the rate at which the distance is changing. Right? And you could say, I don't know how much they want us to say here, but since this is positive and that we know that this is going to be negative, right, from this, that means that the rate is actually slowing, right? Because since my rate would be negative, but the acceleration, if you want, or the rate of change is positive, that means the rate is actually slowing. So like at some point in the storm, it was the water was coming in, but now the rate at which, even though it's still coming in, it's kind of slowing down. This is like the rate of change of the rate. Very physics-y, kind of. I mean, that's one way of thinking of it, I think, probably the best way. Part C. At what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly? Well, I think, again, if you want to know when is it decreasing most rapidly, so that would be when this is at a minimum, right? Decreasing most rapid, that's when that's the most negative, in other words. Most rapidly when f of t is at a minimum, right? The biggest negative number, the minimum. So let's graph it and see. And we're talking about from time 0 to 5. And these rates are negative, so I think we want a negative, let's try negative 10 to 0 and see what that looks like. So it looks like right here, so my cursor is just about in the right place, so I think I'll just use this. So that minimum happens at time 2.840. Hours after the storm began. Right? I don't know, like sometimes I'm really not sure if they want you to, I'll have to look at the rubric, but sometimes they, since this is a closed interval, they want you to say if it's really an absolute minimum, are you sure it's here? Like, couldn't it be at one of the endpoints? And I think looking at the graph, it's like pretty obvious that it's there, so I think probably it's enough to state that. They might want you to check endpoints. You can check the rubric for that. All right. After the storm, a machine pumped sand back onto the beach so that the distance between the road and the edge of the water was growing at a rate of g of p meters per day, where p is the number of days since pumping began. Write an equation involving an integral expression whose solution would give the number of days that sand must be pumped to restore the original distance between the road and the edge of the water. All right, well, that's how much ground was lost, right? We lost 8.505 meters. So if we're going to pump sand back on and we're going to get this many meters per day, then we'll be back to the original when the total that we get here is equal to the amount that we lost. So the total that we get from this, we want to go from 0 to, then go from 0 to whatever, I don't know what we're going to, right? I could use, how about D for the number of days, right, of the g of p function. I want this integral to be equal to 8.505, right? So the integral of the rate of pumping stuff back on would give us how much ground we're making up, the total amount that we make up, right? This is meters per day, so the integral will give us meters, and we want to gain back that much to get back to the original. So that's your solution, right? Where D is the solution. All right.